What if I told you that the sun was constantly shaking, humming and vibrating like a room full of string instruments, but perhaps less melodic?
To understand why, let's take a look at the inside of the sun. Just like the mantle of our Earth, the sun's interior is characterized by constant movement, though instead of magma, it's hot gas known as plasma. This plasma travels in large cells, a movement that creates pressure waves. These waves result in acoustic noise, so the sun really is singing, or at least is trying its best to. Each wave behaves differently depending on the temperature, density, and chemical composition of where it was formed, sometimes appearing on the surface of the sun, like ripples of water when a pebble is dropped. The study of these vibrations is called helioseismology, which is just a big word for the study of quakes on the sun.
We can't hear these quakes on Earth, but we can see them, not by looking directly at the sun, which you should never do, but by using a network of telescopes called GONG, or the Global Oscillation Network Group, which measures these things called Doppler shifts on the surface of the sun. Blue shifts indicate rising regions of the sun, while red shifts indicate sinking regions of the sun. A constant record of these Doppler shifts can map out and document the helioseismic activity of the sun, using this information to map up what the interior of the sun looks like.
These same concepts have also been applied to thousands of other stars across many galaxies, allowing us to identify the temperature and composition of each one, while also predicting if their exoplanets are similar to Earth.
For example, take the red dwarf, Kepler 186. Because of these practices, astronomers were able to identify Kepler 186 as a candidate for the sun, allowing them to also discover its exoplanet, Kepler 186f, which may be a habitable planet.
Not only can helioseismology reveal what's happening on the inside of the sun, but it can also show us what's happening on the opposite side of the sun. Astronomers have figured out that because these waves interact differently with sunspots than with other areas of the sun, we can tell where a sunspot is before that side of the sun rotates to face the Earth.
Why does this matter? Well, sunspots, areas of strong magnetic pressure resulting from areas of tangled magnetic fields, are often joined by solar flares and coronal mass ejections that release huge amounts of intense radiation. At their worst, these can cause disruptions in communication and navigation system and cause blackouts or electricity problems. In other words, not only is helioseismology crucial to our understanding of the internal composition of the sun and other stars, but it also allows astronomers and climate scientists to predict space weather, allowing us to be better prepared for any disruptions in our day-to-day lives. It's safe to say that the sun will never set on helioseismology.